Module 1, Lecture B, Pandas versus Polars. By the end of this lecture, you will be able to explain the key architectural differences between pandas and polars, map common pandas objects and operations to their closest polars equivalents, and evaluate when pandas remain sufficient and when polars is likely to provide clear benefits. Pandas versus polars architecture, memory models compared. When we compare how two libraries manage memory, we focus on how they store, access, and move data in RAM. The older library uses a loose model where each table column is its own object, often backed by numerical arrays, and the table is just a collection of these columns plus an index. This design makes it easy to attach Python objects and mix data types, but it scatters data in memory and sometimes falls back to slower, more memory-hungry Python objects. As a result, the overhead is acceptable for small datasets, but becomes a serious bottleneck in speed and memory efficiency as data size grows. The newer library stores data in a structured, column-based layout, similar to modern databases, using contiguous type buffers in memory. This means values like integers or timestamps are kept in compact blocks, with separate storage for nulls or categories. By organizing data this way, it makes better use of the CPU cache, reduces memory usage, and allows operations such as filtering and aggregation to run more efficiently, much like a database engine. When working with large datasets, how a library manages memory has a big impact on performance. Traditional approaches that store each column separately and allow many mixed types or custom objects can waste memory and even cause out-of-memory errors during complex operations. A columnar model keeps data more compact and efficient, making it better for large-scale analytical tasks. The older, more flexible model is still useful when you need to work with general Python objects or when data size is not a major concern. But as data grows, the structured columnar approach usually offers better speed and resource use. Python code, memory models compared. We want to compare how much memory Pandas tables use versus polars tables, focusing on how object-heavy columns differ from compact, typed columnar storage. By looking at columns that store many Python objects and contrasting them with columns that use efficient, fixed data types, we can see how the underlying memory model affects usage. To make this concrete, we will connect these ideas to simple printed measurements of table sizes, so you can directly observe how different storage approaches change memory consumption. A line that begins with an exclamation mark is a shell command used to install the Python packages Pandas, Polars, and Pyaro. These libraries are needed for working with data and comparing memory usage in the script. This command is usually run in a Jupyter notebook or similar environment to make sure all required dependencies are installed before running the rest of the code. We begin by importing 3 key Python libraries that we will use for working with data. Pandas is used for manipulating and analyzing tabular data. Polars is another data processing library, optimized for efficient handling of column-based data. NumPy provides core numerical tools, including support for arrays and many mathematical operations. Together, these imports give us the main tools needed to handle and compare data across different formats and memory models. We create a variable that stores the value of 1 million to represent the number of rows we want in our simulated data tables. Writing the number with an underscore helps make it clear that it is very large. Using such a large row count is useful for testing how different data storage methods handle memory when working with a substantial data set. We create a Pandas DataFrame that simulates a large dataset with 1 million rows, where each row has a single column called City containing the text New York. This uses a flexible object type for storing strings, which makes the text data easy to work with, but not very memory efficient. This simple setup lets us compare how different ways of storing the same data affect memory usage. In this example, we create a Pandas data frame with a city column and store it using a categorical data type instead of regular strings. A categorical type encodes repeated text values more efficiently, which helps save memory. This is especially useful for large datasets where many rows share the same city names. By using categorical data instead of standard object types, we significantly reduce the memory footprint of the data frame. We build a Polars data frame with a single column called City that contains 1 million entries of the string New York. Polars stores this column using its efficient UTF-8 string type. This type is optimized for compact storage of text data, so it uses memory more efficiently than more flexible but heavier data types. We use a helper function called showSize that takes a label and a memory size in bytes, then converts that size into megabytes. It does this by dividing the number of bytes by 1024 squared. This conversion makes memory usage easier to understand in a human-readable form. The function then prints the label and the converted size in megabytes, formatted to 2 decimal places, to clearly display how much memory is being used. To measure how much memory a Pandas data frame with object columns uses, you call its memory usage method. You enable the deep option so it counts all memory used by the underlying objects, not just the data frame structure. Finally, you add up the reported memory values to get the total memory consumption, including the overhead from the data frame index. This line measures how much memory a Pandas data table uses when it includes a categorical column. It also counts the overhead from the table's index. By calling the memory usage method with the deep option set to true, it includes the memory used by the actual data, not just the container. Finally, the sum operation adds up the memory from all parts to give the total size in bytes. The code estimates how much memory a Polars data frame uses by calling a built-in method that reports its approximate size in memory. This gives a useful approximation of the data frame's memory footprint, showing how much memory it is consuming. This measurement is then used as part of a larger comparison of memory usage across different data storage formats. The code begins by printing a clear header that introduces the upcoming memory usage comparison results. This header prepares the listener to understand how different data storage methods affect memory consumption. It focuses specifically on storing 1 million rows of city data. By setting this context first, it makes the detailed memory figures that follow easier to interpret. We use a helper function called showSize to report how much memory a Pandas data frame with an object-based column layout is using. This function takes a descriptive label and the memory usage in bytes as inputs. It converts the byte value into megabytes, and then prints the result together with the label. This makes it easy to see how much memory that particular data frame configuration consumes. We use a helper function to display the memory usage of a Pandas data frame that includes a categorical column. This function takes a descriptive label, in this case, identifying it as a Pandas categorical column, and the memory size in bytes. It then converts the size from bytes to megabytes and prints a formatted message. This tells us how much memory the categorical data frame consumes in a clear and readable way. We use a function to display memory usage by giving it a label that describes the data structure, such as a Polars UTF-8 column, so we can recognize the output in the console. We also pass in the value that represents the memory size of the Polars data frame. The function converts this size from bytes to megabytes and then prints it. This makes it easy to see and compare how much memory the Polars data frame uses. This script compares how much memory is used when storing 1 million city names in Pandas and Polars data frames, focusing on how data types affect efficiency. It first shows that a standard object column in Pandas is very memory intensive. It then switches to a categorical column in Pandas, which uses less memory thanks to encoded values. Finally, it builds a Polars data frame with a compact text column, which turns out to be the most memory-efficient option. The printed memory usage confirms that Pandas with object types uses the most memory, Polars uses the least, and Pandas with categorical data falls in between, highlighting how important data type choices are for large datasets. Row versus columnar. Pandas and Polars mainly differ in how they store data in memory. Pandas is row-oriented, keeping all the values for each record together, which works well when you need to handle complete entries such as full log lines or survey responses. However, this layout can be inefficient when you repeatedly operate on a single column across many rows, like computing an average. Polars is column-oriented, storing each column's values together, which makes these column-wise operations faster and more efficient. Polars stores data in a columnar layout, where all values of each column are kept together in memory. This design is well suited for analytical tasks that work on entire columns, such as aggregations and filtering. Because the processor can read large continuous chunks of column data efficiently, it makes better use of the cache and vectorized processing. As a result, operations like summarizing many transactions or filtering large log files can run much faster and use less memory in Polars than in row-oriented systems. When choosing between Pandas and Polars, think about how you work with your data. If you often access or update whole records, such as processing orders or validating datasets, Pandas is usually more intuitive because it is row-oriented. For large analytical workloads, like scanning big marketing or sensor datasets, Polars tends to be faster thanks to its column-based design. This design allows efficient scanning and manipulation of columns, better use of the processor cache, and more vectorized operations, especially when working with millions of rows. Parallel execution model. These two libraries differ mainly in how they run your code. One executes operations eagerly in a single thread on one CPU core, which is simple but cannot take full advantage of multi-core processors. The other builds a plan of transformations as an operation graph, and then schedules work across multiple cores. This parallel execution strategy allows it to run tasks more efficiently. When processing a large dataset of customer transactions, a single-threaded system runs each operation one after another on one core, which becomes inefficient at scale. A parallel execution model instead splits the work into independent pieces that multiple cores can handle at the same time, such as processing different regions in parallel. The engine coordinates these parallel tasks and then merges their partial results into one final output. This makes much better use of all available cores while keeping the high-level operations the same from the user's point of view. In a parallel execution model, the query engine plans and optimizes the entire sequence of operations to run efficiently. It can reorder steps and push filters earlier so less data needs to be processed. Combined with multi-threading, this makes tasks like processing sensor data or analyzing web logs much faster and uses hardware more effectively. Overall, it speeds up large data workloads while letting users keep a high-level, declarative style for their analysis. Python code, parallel execution model. We want to compare how long similar operations take in Pandas and in Polars, and to highlight how their execution models differ. The goal is to show a simple timing difference between the two libraries using the same kind of task. We also want to conceptually contrast single-threaded execution with parallel execution, without going into low-level details. To keep the demonstration practical and fast to run, we will use a medium-sized dataset rather than a very small or extremely large one. A shell command, starting with an exclamation mark, is used in environments like Jupyter Notebooks to install the Python libraries Pandas, Polars, and Pyaro. This ensures they are available for the script that follows. Pandas is a popular library for data manipulation and analysis. Polars is a fast DataFrame library for Rust and Python. And Pyaro is used to work with columnar data formats. Installing these libraries is essential for comparing the performance of Pandas and Polars in the script. We begin by importing the time module so we can measure how long our operations take. Then we load the Pandas library for data manipulation and analysis. We also import the Polars library, which is another data tool designed to be fast and efficient, especially with large datasets. With these imports in place, we have the tools needed to work with data and compare the performance of Pandas and Polars. We begin by choosing a dataset size of 2 million rows, which we refer to as the row count. This large size makes the upcoming operations realistic and ensures that performance differences between data processing libraries are noticeable. Using a substantial dataset helps us meaningfully compare how efficiently each library handles the same workload. We begin by creating a simple Pandas DataFrame with two numeric columns named A and B. Each column holds a sequence of numbers starting at 0 and increasing up to just under 2 million. This large but straightforward dataset serves as a convenient basis for demonstrating different operations. It also allows us to compare how various data processing libraries perform on the same numeric data. The function first keeps only the rows where the value in column A is even, narrowing the data to a specific subset. It then adds a new column called C by multiplying the values in A by 1.5 and adding the corresponding values in B, creating a new metric. After that, it groups the data based on the remainder when A is divided by 10, forming up to 10 groups. For each group, it computes the average of the new C values. The function returns this grouped summary as a compact view of the processed data. To measure how long our Pandas operations take, we first record the current time as a starting point. We then run a function that performs several data manipulations on a Pandas DataFrame, such as filtering, enriching, and grouping the data, and it returns the final result. After these operations finish, we record the current time again. By subtracting the start time from this end time, we obtain the total elapsed time, which tells us how long the Pandas operations took and helps us assess their performance. We begin by converting a Pandas data frame into a Polars data frame using the appropriate conversion method from the Polars library. This step allows us to take advantage of Polars features, especially its ability to process data in parallel. By moving the data into Polars format, we set it up for faster and more efficient operations. This preparation is important when we expect later steps to benefit from Polars' optimized execution model. We define a function that uses Polars by first turning the input data frame into a LazyFrame, so computations are deferred and can be optimized. We then keep only the rows where column A is even and add a new column C, defined as 1.5 times column A plus column B. Next, we group the data by the remainder of column A when divided by 10 and compute the average of column C for each group. Finally, we collect the results, which runs all the lazy operations and returns the final data frame. To measure how long our Polars operations take, we first record the current time using the time module. We then run the function that performs all the Polars processing on the data frame, using Polars' lazy evaluation to optimize and parallelize the work. After the operations finish, we record the time again and subtract the start time to find the elapsed duration. This measured time can then be compared with the time taken by the Pandas operations to evaluate their performance difference. We first print how long the Pandas operations took, rounding the time to 3 decimal places, and then do the same for the Polars operations so we can directly compare their execution speeds. Next, we report how many rows are in the Pandas result by checking its length, and how many rows are in the Polars result by using the height of its data frame. Finally, we preview the first few rows of the Pandas result and then the Polars result, using each library's head method to quickly inspect a small sample of the output and verify that the results look correct. This script compares how quickly Pandas and Polars handle data operations on a dataset with 2 million rows. It runs similar tasks in each library, including filtering, adding a new column, and grouping based on a modulus calculation. Pandas performs these operations in a single thread, while Polars can use multiple cores for parallel execution. When you run the script, it reports the time each library takes and shows a small preview of the results. Both libraries produce the same number of output rows, but Polars usually finishes the work faster. Pandas to Polars mapping. Data frame concepts compared. When moving between data libraries, it helps to think of a data frame as a simple table with rows and columns that you use to load, inspect, transform, and analyze data. Both libraries rely on this central object and support similar operations, such as filtering and joining. One library may treat the data frame more like a flexible spreadsheet, while another treats it as a more rigid data table. But the basic idea is the same. In all cases, you start by reading data into a data frame and then apply transformations to reach your analytical goals. Across different data libraries, the idea of a data frame is very similar, so many tasks feel familiar even if the syntax changes. Whether you are working with a large table of online orders or any other dataset, you can still select certain columns, filter rows, create new columns, and group by a category to compute totals and counts. These actions keep the same meaning across libraries, so you are really performing the same high-level data transformations in slightly different styles. When working with complex workflows that use many data frames, it is important to have a clear mental model of how they relate. In both data libraries, you often join tables, stack them, and reshape them between wide and long formats. For example, you might link patient demographics to lab results using an ID, or combine monthly marketing data into a yearly table and pivot it for regional analysis. These operations are conceptually similar across ecosystems, so you can transfer your existing understanding while learning new syntax. Recognizing these parallels helps you organize and streamline your data workflows more effectively. Series, index, and columns. The main difference between these two libraries is how they treat series, indexes, and columns. The traditional library relies on a dedicated index that is tightly integrated with series operations, such as aligning data by labels or using the index as a time axis. The newer library instead focuses on columns, treating each column as a series and not using a separate index object. In this newer approach, rows are identified by their position or by specific columns. So you define which columns act as keys or determine order, rather than relying on a special index structure. When working with daily sales data in a column-focused library, you no longer rely on the index for tasks like slicing by date or automatically aligning datasets. Instead, dates, store identifiers, and categories are stored as regular columns. You perform selections, filters, and joins by explicitly referencing these columns and specifying the join keys and conditions. This shifts your mindset from depending on implicit index alignment to clearly defining relationships through specific columns. In an index-centric approach, each series has its own name and index, can be manipulated on its own, and is later aligned back into a data frame using that index. In a column-centric approach, a series is treated mainly as a column inside a data frame, and you apply transformations directly to these named columns. For example, when you compute a new metric, such as customer lifetime value, you work with the existing column names and store the result as another column. This treats the data frame as one unified structure, where each series is just part of the whole, and row identity comes from explicit keys or row positions rather than a separate hidden index. Python code, series, index, and columns. Pandas and polars differ in how they think about data access and labeling. Pandas relies heavily on an index for row labeling, selection, and alignment, which can sometimes introduce hidden behavior when the index changes or is not what you expect. Polars instead focuses on explicit column keys, so you work more directly with columns and avoid much of the implicit index logic. When comparing the two, it is helpful to highlight how row selection and data alignment in Pandas often depend on the index, while in Polars, they are driven by clear, visible column references. This encourages a more explicit and predictable style of data manipulation. The line with the exclamation mark is a command used to install the Pandas and Polars libraries. It is typically run in a command line or notebook environment. This step ensures both libraries are installed and available before you run the rest of the script. In other words, it prepares the necessary tools so the code can execute correctly. We begin by importing two data processing libraries, Pandas, which is widely used for data manipulation and analysis, and Polars, which is known for its speed and efficiency. Using both libraries side by side lets us compare how they handle data structures. In particular, we will focus on how each one manages indices and columns, and highlight the key differences between their approaches. We create a Pandas DataFrame to hold sales data with columns for dates, store identifiers, and sales amounts. Next, we set the date column as the index so that each row is labeled by its date, rather than treating the date as a regular column. Using dates as the index makes it easier and more efficient to select rows and align data based on specific dates in Pandas. We begin by working with a Pandas DataFrame that uses the date as its index, meaning the date values label each row instead of appearing as a regular column. A short message is printed to explain that the data frame is indexed by date, and then the data frame itself is shown. This example emphasizes how Pandas can manage row labels implicitly through an index, which may differ from how other libraries, like Polars, represent similar data. We begin by announcing that we are selecting a row in a Pandas data frame using an index label to set the context for the operation. Then, we use the location-based selection method in Pandas to access a specific row, whose index label is the date January 2nd, 2024. This shows how Pandas lets you directly select rows by their index labels, which contrasts with libraries like Polars that focus more on explicit column handling rather than implicit index-based access. We build a Polars data frame to store sales data with 3 columns: date, store, and sales. The date is kept as a normal column instead of being used as an index. This design gives us clear, explicit control over how we manipulate and filter the data. It contrasts with Pandas, where the index can sometimes hide how the data is organized. In this example, the Polars data frame is displayed with the date kept as a normal column instead of being used as an index. This emphasizes that Polars treats all fields as explicit columns, unlike Pandas, which often hides the index. Seeing the full data frame makes the structure of the data clear and keeps the date visible. This can make tasks like filtering and selecting data by date more straightforward. Here we use Polars to filter a data table by a specific date, keeping only the rows where the date column matches January 2nd, 2024. The filter operation is applied directly to the sales data and explicitly checks the date column. This illustrates how Polars focuses on clear, column-based operations rather than relying on the kind of hidden index behavior that is common in Pandas. We display the result of a Polars data frame operation, introduced by a short message that explains we are selecting data based on a specific column. The printed result shows only the rows where the date column matches a chosen value. This demonstrates how Polars uses explicit column-based filtering, making it clear which column drives the selection. It also contrasts this approach with Pandas, where filtering often relies on a hidden index instead of directly specifying the column. This script compares how Pandas and Polars handle data indexing and column selection. In Pandas, the dates are stored as a hidden index, so you can select a specific row directly by its date label. In Polars, the date remains a visible column, and you select the same row by filtering on that date column. This difference shows that Pandas leans on index labels for row selection, while Polars emphasizes explicit column-based operations. Running the code makes these contrasting approaches to data manipulation clear in practice. LazyFrame query plans. When moving from Pandas to Polars, it is important to understand that Polars uses a different execution model based on LazyFrame query plans. In Pandas, each operation, such as filtering or aggregation, runs immediately and creates new data structures at every step. In contrast, Polars records these operations in a LazyFrame as a planned sequence, then optimizes and executes them only when you finally request the result. This means LazyFrame serves as a blueprint that lets Polars streamline and speed up data transformations before actually processing the data. When cleaning large monthly sales data, a typical Pandas workflow creates many intermediate tables as you load, clean, filter, compute revenues, and group by product, which can use a lot of memory. Polars handles this differently by letting you define these steps as transformations in a LazyFrame that does not run right away. Instead, it builds a query plan that represents the whole pipeline. This plan is then optimized and executed only when you finally request the result. Much like how a database query planner works. As a result, you get better performance without having to manually optimize each step. A LazyFrame query plan in Polars is like a streamlined version of a Pandas pipeline, but with an optimizer that makes it more efficient. Instead of splitting complex data tasks, such as web log analysis or sensor processing, across multiple scripts, you can express them as one continuous lazy query. This single plan lets Polars minimize redundant work and operate only on the data that is truly needed. By treating all your transformations as one cohesive workflow, LazyFrame combines the familiar style of Pandas with optimized execution. So you should aim to express your entire workflow as a single lazy query for best performance. Choosing Pandas or Polars. Quick, exploratory workflows. When you are quickly exploring data, speed matters more than theoretical performance. And Pandas is often ideal for small to medium datasets that fit in memory. It lets you easily inspect columns, check for missing values, and generate basic summary statistics or quick plots. Because its syntax and execution model are straightforward, you can focus on the analysis instead of wrestling with complexity. Its smooth integration with plotting tools and notebook environments makes Pandas a strong choice for early-stage data analysis. When exploring very large datasets, Polars can keep your analysis fast and interactive, where Pandas might slow down. Its optimized engine and lazy query planning make operations like filtering and aggregating much more responsive, even with massive data, such as transportation logs or clickstream records. This lets you quickly try different user definitions or time windows without long waits. Overall, Polars helps you maintain a smooth analytical workflow by keeping operations quick and minimizing interruptions to your thought process. Choose between Pandas and Polars based on how fast and large your data exploration needs to be. Pandas is a good default, especially when you are first learning a dataset or collaborating with others who already use it. If you find yourself constantly sampling data, avoiding complex queries, or struggling with performance, Polars may be a better option. Many people start with Pandas for initial exploration and move to Polars as their work grows more demanding. The main goal is to keep your workflow fast and iterative by using the tool that best matches how you think and explore data. Scaling complex pipelines. When you move from small analyses to large, complex data pipelines, the differences between Polars and Pandas become important. Polars lets you define pipelines as declarative transformations, then optimizes and runs them efficiently across multiple cores and with streaming data, which improves performance and memory use. Pandas executes each step eagerly on a single core, which is usually fine for moderate data, but can slow down or strain resources in bigger workflows. The key issue is not just how large your dataset is, but how often you run the pipeline and how much slower or less reliable runs affect your work. A data engineering team might run a daily analytics pipeline that cleans and enriches raw logs to power dashboards and machine learning features. If they use Pandas, each step builds full data frames in memory and runs joins and group operations one after another without much optimization. This approach can work on small data sets, but as the data grows to millions of rows and the transformations become more complex, the pipeline slows down and becomes harder to manage. Polars addresses this by using a lazy execution engine that optimizes the whole chain of operations, cuts unnecessary data handling, and uses multiple cores in parallel, leading to a faster and more scalable pipeline. You do not always need to replace Pandas with Polars for complex data pipelines. If your data is relatively small, processed infrequently, and your current Pandas workflow runs reliably, the cost of retraining and rewriting may not be worth it. However, if your data volume is growing, you have strict time requirements, or many users depend on the pipeline, Polars can help improve performance and scalability. In the end, the choice depends on whether your existing tools are limiting speed, reliability, or long-term maintainability. Python code. Scaling complex pipelines. In this lesson, we will compare how to scale complex data processing pipelines using both Pandas and Polars side by side. We will use the same transformation steps to show the difference between eager execution, where operations run immediately, and lazy execution, where work is planned and optimized before running. As we increase both the complexity of the pipeline and the size of the data, we will highlight how the runtime performance of these approaches changes. This will help you understand how execution mode and library choice affect scalability for large and complex workloads. A line starting with an exclamation mark is a command that installs the Polars and Pandas libraries. It is usually run in a Jupyter notebook or similar environment to make sure these libraries are available. By downloading and setting up the required packages, it prepares the environment so the rest of the code can run without errors caused by missing dependencies. In this script, we import pandas and polars to handle and transform data, and we also import the time module to measure how long these operations take. Pandas is used for working with data frames in a traditional eager style, where operations run immediately. Polars offers a lazy execution approach, where it plans and optimizes the data processing steps before running them. By timing these pipelines, we can compare how efficiently pandas and polars handle more complex data transformations. The function first generates a sequence of dates starting on January 1st, 2024, for a given number of days. It then builds lists of store names and product names by numbering them. Next, it sets up a dictionary to hold the sales data with entries for date, store, product, units sold, and unit price in US dollars. Each entry is stored as a pandas series filled with missing values, or zeros, and indexed over the total number of rows, which is the number of days multiplied by the number of rows per day. This structure serves as a template for later filling in synthetic sales data. We build the dataset by starting with an index at 0 and looping over each date, then for each date, looping over the required number of rows. At each step, we fill the current row with the date, a store name chosen by cycling through the store list, and a product name chosen by cycling through the product list. We then set units sold based on the index so that it repeats in a pattern from 1 to 50. And set the unit price in dollars based on the index so that it repeats in a pattern starting from 5. After filling these values, we increase the index to move to the next row and continue until all rows are populated. This function returns a Pandas DataFrame built from a dictionary of synthetic sales data. The data includes columns for date, store, product, units sold, and unit price in US dollars. Each column is stored as a Pandas series, which supports efficient data manipulation. Using a data frame makes it straightforward to work with this tabular data and to perform common analysis tasks, such as filtering, grouping, and aggregating. We start by generating a synthetic dataset that simulates daily sales logs. Using a data generation function, we create sales records for 60 days. For each day, we produce 2,000 rows of data. This gives us a moderately sized dataset that is suitable for testing how well our data processing pipelines perform. The code converts each column of the Pandas data frame to specific NumPy-backed data types, so that converting it to a Polars data frame does not require PyArrow. It sets the date column to a datetime type with nanosecond precision and treats the store and product columns as object types suitable for categorical values. It also casts units sold to a 64-bit integer and unit price in dollars to a 64-bit floating point number. These choices optimize the data frame for efficient processing and better compatibility with Polars. We convert the Pandas data frame into a Polars data frame so we can directly compare how the two libraries handle the same data. This lets us examine both performance and execution style side by side. Polars is especially strong with large data sets because it uses lazy execution to optimize the processing pipeline before running it. By doing this conversion, we prepare a fair comparison of how each tool processes identical information. The function first filters the data to keep only rows where more than 10 units were sold, creating a smaller set to work with. It then computes revenue in US dollars by multiplying units sold by unit price and stores this as a new column. After that, the revenue is adjusted 3 times in sequence. It is increased by 5%, then decreased by 3%, and finally increased by 2%. Each adjustment updates the same revenue values, so the final column reflects all of these percentage changes applied one after another. The code groups the data by date and store, then calculates the total revenue in US dollars for each combination. This produces the total revenue per store for each day. It then sorts these results by date and store so they are easier to read. Finally, it keeps only the top 5 rows from the sorted data and returns them for further analysis or display. We create a LazyPolars data frame so we can define all our transformations before anything is actually executed, allowing the system to optimize the whole pipeline. We then filter the data to keep only rows where units sold are greater than 10. Next, we add a revenue column in US dollars by multiplying units sold by the unit price. After that, we increase this revenue by 5%, then decrease it by 3% to simulate additional adjustments such as taxes, fees, or discounts. All of these steps are stored in the Lazy execution plan and run efficiently only when needed. The code adjusts the revenue values by multiplying them by 1.02, then groups the data by date and store to calculate total revenue for each combination. It then sorts these grouped results by date and store so the output is easier to read. After sorting, it selects only the first 5 rows to provide a concise summary of the most relevant records. Finally, it runs all these steps and returns the completed transformed data. We measure how long the Pandas pipeline takes to run by recording the current time before and after its execution using a performance counter from the time library. First, we capture the start time, then run the pipeline function on the prepared Pandas DataFrame, which processes the data eagerly, so each step is executed immediately. After the pipeline finishes, we capture the end time and subtract the start time from it. The result is the total execution time of the Pandas pipeline, giving us a measure of the cost of this eager execution approach. To measure how long the Polars pipeline takes to run, we first record the current time using a performance counter. We then execute the Polars pipeline, which uses lazy execution so that operations are optimized and only run when necessary. After the pipeline finishes, we record the time again and subtract the start time from the end time to get the total execution time. This measured time can then be compared directly with the execution time of the Pandas pipeline. We measure and display the runtime of the Pandas pipeline, rounding the time to 4 decimal places for clarity, and then do the same for the Polars pipeline, so their performance can be easily compared. After reporting the runtimes, we show sample rows from the Pandas pipeline output, which contains aggregated data. We then repeat this step for the Polars pipeline, printing a message and displaying its sample results. Together, These outputs let us compare both the execution time and the resulting data from the two different processing methods. This script compares the performance of eager and lazy execution in data processing pipelines using pandas and polars. It creates synthetic sales data over 60 days and runs it through a pandas pipeline that processes each step immediately, and a polars pipeline that builds a lazy plan and optimizes it before running. When executed, the polars pipeline usually finishes faster because of this optimized lazy strategy. The script reports the runtime of each pipeline and shows a sample of the aggregated results so you can directly compare their efficiency and outputs. Hybrid Pandas Polars workflows. You can combine pandas and polars in one workflow to use the strengths of both libraries. Start with data in pandas as it already fits into your existing scripts or tools. Then hand off heavy tasks like large joins or aggregations to polars for better performance. After the intensive processing is done, you can convert the results back to pandas for visualization and reporting. This hybrid approach lets you improve speed and efficiency without having to replace your entire current system. Hybrid workflows are useful for complex data pipelines that rely on multiple tools and teams. A research group that already uses pandas and a machine learning library expecting pandas data does not need to switch everything to polars. Instead, they can keep initial processing and final modeling in pandas, but move the heavy, performance-critical transformations into polars. The data flows from pandas into polars for efficient processing, then back into pandas for modeling and visualization. This approach gains polars speed while preserving existing tools and workflows. When using pandas and polars together, you should balance the cost of moving data between them against the performance benefits. A hybrid approach works well when polars handles the heavy group operations and complex calculations, while pandas is used for lighter tasks such as filtering and visualization. This is especially useful in areas like finance or web analytics, where a few intensive transformations dominate the workload. As you gain experience with polars and your data grows, you can gradually shift more processing to polars or keep a mixed setup that optimizes both speed and compatibility. In this lecture, you learned to explain the key architectural differences between pandas and polars, map common pandas objects and operations to their closest polars equivalents, and evaluate when pandas remains sufficient and when polars is likely to provide clear benefits. In the next lecture, Lecture C, we will go over setting up polars. Thank you for your attention. See you all in the next lecture.